I'd like you to imagine an end user who's gone out and purchased a couple of used wireless routers. There's a D-Link, there's a version from Cisco, and maybe he paid like 20 bucks US for them used. Now, furthermore, I'd like you to imagine this user, we'll call him Bob for this example. I'd like you to imagine him bringing those into the office. And so let's say this is Bob's cube right here. And let's say this is his wall jack, where it's his RJ45 connection. In the wall, it goes probably up to the ceiling, over to the wiring closet, and eventually down to a switch port that he's connected to. And normally Bob's computer would connect to that. But today Bob brought his device in and thought, you know what, I want to plug a couple extra things in the network. So what he did was he took one of the 4 switch ports on the back of this D-Link router and plugged it into the wall jack. And then Bob took his PC and plugged the PC into another switch port. And on many of these devices, they auto-sense the actual cabling. So now Bob is sitting here at his computer, and he has access to the rest of the network. He's happy. What's the problem with this scenario? Well, besides breaking a whole bunch of rules I'm sure are currently at the company about plugging in unauthorized devices, Bob also has introduced to the network a brand new DHCP server. Because by default, these devices are acting as DHCP servers. So now let's introduce Sally. So here's Sally and her PC. And when Sally's computer boots on the network, it's going to go ahead and ask for a DHCP assigned address. Now, the DHCP process has 4 major steps, and they are DORA. There's a discover packet, there's an offer, a request, and the acknowledgement. Now, the client is going to do the discover, and the client's also going to send a request. And the DHCP server, I'll put those in red, the server is going to do the offer, and the server is also going to do the acknowledgement. So if we have Sally here, and we have the server here, the conflict that we're going to have is which DHCP server is Sally going to get an IP address from? The D-Link that Bob brought in, or the one from corporate? So it'll go something like this. Sally will make a DHCP discover. One or more servers will make an offer. Sally will see that IP address and say, you know what, that sounds great. I'd like to request that IP address. So here's our discover and our request. Here's the offer from the server. And once Sally does request that IP address, the server is going to finalize that with an acknowledgement. Now, unfortunately, if it was Bob's D-Link device that handed out the IP address to Sally, she is all dressed up but has nowhere to go because she's got an IP address. She's been given a default gateway, which is very likely the D-Link's address. However, the D-Link doesn't have any kind of connection to its WAN port. It has nowhere to go. And in addition to Bob bringing on this rogue DHCP server on the network, he's also very likely introduced a wireless network that is unprotected. So as customers try to connect to wireless networks, if they connect to the D-Link over wireless, they'll be in the same boat as Sally, being given an IP address through DHCP. And if this D-Link acts as their DHCP server, those clients are not going to have successful interaction on the network. And that same negative consequence also could apply to Bob. When Bob booted up, his PC needed an IP address. And if Bob's PC got an IP address from the D-Link rather than the corporate DHCP server, Bob also wouldn't have any success in getting through the network. And this is an example of an accidental rogue DHCP server, one that's not authorized by the company. If we had someone who was malicious with a DHCP server, it could go much, much worse. Now, let's say we had a malicious person coming in who wanted to take advantage of our system by implementing a rogue DHCP server. And I'm going to resist the temptation to talk about wireless because there's a whole bunch of other cool stuff they could do with wireless as well. But just for this discussion, we're taking a look at the just rogue DHCP server function. The first thing they might want to do is get a connection to a switch port. And that could be from an existing office or if they got physical access to the wiring closet. It really doesn't matter because there's a lot of physical access that's available. Because almost every cube in every office has an RJ45 jack that he could plug into. Or if it's Bob, let's say it's Bob himself, the employee, a disgruntled employee going to do some illegal things. Maybe it's Bob and he's using the wall jack in his own office. The first thing that Bob might want to do is go ahead and do something called a DHCP Starvation attack. So for example, if this is network 10.123.0.0/24, and let's say all these ports for this discussion belong to the same VLAN, and we'll call it VLAN 123. How many IP addresses in this subnet could a valid DHCP server hand out? It's very likely we have a static IP address for the default gateway. So there's one that's gone. And we have 253 other possible IP addresses that the DHCP server could hand out. So with a DHCP starvation attack, Bob sends a whole bunch of DHCP discover packets into the network, and what he does is he makes up bogus source MAC addresses. And with this attack, what Bob's thinking is, if he can make 253 requests, and he can trick the DHCP server into allocating the rest of the IP addresses in the subnet to Bob, that means that the real DHCP server now has no other IP addresses to hand out. Its supply of DHCP assigned addresses has been exhausted. It's also sometimes referred to as a DHCP exhaustion attack. We're exhausting or using up all of the IP addresses that DHCP server has to offer. And if you'd like to see an example of a DHCP starvation attack, I would refer you to the DHCP starvation attack video, which is in the penetration testing course, which is focused around Backtrack and Kali Linux. So if you want to see a whole video just on how to implement a DHCP starvation attack, that's the place to go. So that would be Bob's first step. Number one, starve out the IP addresses from the DHCP server. Secondly, Bob would go ahead and introduce his own DHCP server. And Bob's DHCP server could be handing out the IP addresses from that same subnet, or check this out, any subnet. Because this VLAN is a layer 2 broadcast domain. If Bob and his rogue DHCP server want to start handing out a different range of addresses, maybe Bob's DHCP server could hand out 192.168.0.0/24. Because the clients who connect, like PC1 and PC2, they don't know. All they're doing is they discover, there's an offer made, they request it, there's an acknowledgement, and inside that DHCP information includes things like the DNS server to use, the default gateway to use, and so forth. So here's the cool thing. If Bob's device is acting as the DHCP server, he can hand out any subnet that he wants to, and he can hand out any DNS information that he wants to, and it's very likely for the default gateway it hands out, it's going to be Bob's address. So now when PC1 and PC2 connect, they might be given an IP address on this new subnet. They don't care. And when they try to get off of the local subnet, they use their default gateway, which is Bob's device. And as a courtesy, Bob would have configured his DHCP server also to act as a router, who could then forward it to the valid default gateway, which is maybe 10.123.0.1, and forward it on its way. So in that case, Bob's device would be acting as a DHCP server, a router, and Bob would be performing something called a man in the middle attack, or MITM. Because now all the traffic from PC1 as it goes out to the internet or wherever it goes, if it's going through the default gateway, which is Bob's device, Bob now has access to see all of that information. And the tricky part is this, PC1 and PC2 may not have any clue that that's even happening. They go to Google, they go out to the internet, it works. They might be completely oblivious to the fact that it's happening. So what can be done? Well, have no fear. What we can do to help reduce the risk of a rogue DHCP server, whether it's implemented maliciously or accidentally, is we can implement DHCP snooping. Here's a packet capture that includes a DHCP conversation. And let's clean this up just a little bit. We're going to type in the filter bootp, which is the old name for the current DHCP. And we'll press enter to implement that filter. And here are the 4 primary packets involved in typical DHCP. We have the discover packet, and that's from the client going towards the server. We have a DHCP offer, and that's going from the server to client. The client gets that offer and says, holy shnikers, I've got a DHCP offer. And it requests it, says, you know what, I love that IP address. It's perfect, I'll take it. So that's also from the client back to the server. And then once the client does that request, the server follows it up with an acknowledgement, which is also sent from the server to the client. And here's what DHCP snooping does for us. On the switch, when we enable DHCP snooping, let's say that all these ports are in the same VLAN for this discussion, the default attitude for DHCP snooping, once it's enabled for a switch and for the VLAN, is no. Meaning, I don't trust any ports on this switch regarding DHCP. So what happens if Bob is sitting here on this port right here, and if Bob tries to send a server message, like an offer or an acknowledgement, into the switch, it's like there's a little firewall or a bodyguard at that switch port that says, hey, wait a sec, Bob, I don't trust your port. You're trying to send a DHCP server type message into the network? No, it's not going to happen. And that frame is then dropped. The switch does not let that frame come into the network. So we'd simply have a whole bunch of untrusted ports on the switch from a DHCP snooping perspective. So this is Lois, here's Kurt, here's Sean, here's Laura, and the list goes on. And if any one of these untrusted ports tries to send a server-to-client type of message into the network, because they're untrusted ports, DHCP Snooping says, nope, I'm not going to forward that frame into the switch. Now, on the other hand, if they send in discover messages and request messages, client type of traffic, from a DHCP perspective, the switch is perfectly happy to forward those, because discover messages and request messages are typical things that a real client would send in the network. Now, the challenge with this is, what if we have a real DHCP server, the authorized one from the company, on this port right here? And let's call this port 11. Well, if the DHCP server tries to send DHCP server messages into the network, the switch, because this port is untrusted by default, is going to say no. And that's why we would take special care on any ports that are connected to DHCP servers, and we would configure them as DHCP Snooping trusted ports. And a trusted port simply says, oh, that's okay then. Even though every other port in the VLAN by default is untrusted, a trusted port on the switch will allow the offers and the acknowledgments and other server-to-client type messages from a DHCP server to come into the network. So now if Bob brings in from home his D-Link or other device and tries to become a DHCP server, the switch right there at the switch port will not allow those server-type messages to enter the switch, and as a result, we've just mitigated and protected against a rogue DHCP server. So while we're on this diagram, let's say that we have an uplink right here. So let's say it's a trunk that goes over to another switch. And on that switch, there's a whole bunch of other ports as well. And what if, for fault tolerance purposes, we have a DHCP server here, and we also have a DHCP server over here? Well, the challenge is, by default, all of the ports on the switch, including this trunk port, is a DHCP Snooping untrusted port. If we ever do want this DHCP server to send server messages to devices in this network, we would also have to configure this trunk port as well as a trusted port. And if we extended it one further and we had another switch and there was another trunk link, we'd also want to configure the trunk port there as a trusted port if it led off to another valid DHCP server. So the key is, anywhere that you want to allow DHCP server messages to come into a switch, that port needs to be configured as a DHCP Snooping trusted port. Otherwise, it's going to deny anything that looks like server-based traffic. For those of you who are interested in Wireshark specifically and want to learn more about the details of using filters and using Wireshark effectively, I would encourage you to check out the Wireshark course right here available for you at CBT Nuggets. It's included as part of your membership. And it is time, my friend, for the assessment check. So take a moment. If you need more time during the music, simply pause it, answer these questions, and then when you're done, we'll compare notes. Good luck. All right, let's check our work. Question number 1 reads, regarding DHCP snooping, if that feature is enabled on a catalyst switch, what is the default state of a port regarding DHCP snooping? And if you said, Keith, by default, it is an untrusted DHCP port. If that's your answer, excellent. Question number 2, which DHCP packet types are allowed in on a trusted port? And the answer to that is every type of DHCP packet, whether it's server-based or client-based. If it's a trusted port, it's not going to be stopping DHCP packets of any type. It's an untrusted port that denies and will not allow server-type DHCP messages and packets to be sent in. So a trusted port is wide open from the perspective of what types of DHCP packets can be seen. And question number 3, what are 2 port types that may need to be trusted with DHCP snooping? And the 2 answers that I'm looking for that we covered in this nugget are access ports, which connect directly, for example, to a DHCP service. And if that DHCP server is not on the same local switch, but it's in the same VLAN, that also may need to go across a trunk. So we may have a trunk that needs to be a DHCP trusted port as well. As we take a look at the problem of rogue DHCP servers, one of our tools that we now know we can use is the concept of DHCP snooping, with the default attitude of untrusted or non-trusted DHCP ports. And that can help mitigate the threat of a rogue DHCP server. And what we'll do is we'll have a separate nugget on a demonstration of the implementation and verification of DHCP snooping. So I hope to see you in that video as well. Meanwhile, I hope this has been informative for you, and I'd like to thank you for viewing. There's a couple really important aspects regarding using good security. The first is to be aware that it exists, and the second would be to put it to work. So in a previous nugget, we took a look at the concepts of DHCP snooping, and together, you and I in this nugget will take a look at an example of implementing DHCP snooping. Let's begin. So to increase the impact of the reality of this scenario, let's take this computer right here. Let's say this is Lois's computer, and she is on the 10.123.0.0/24 network. The default gateway is 10.123.0.1. That's also acting as the DHCP server, and it also happens to be acting as a DNS server. So when Lois booted her machine up, she went out to the internet, and let's say she went out to cbtnuggets.com, and it worked, and she's thinking, hey, everything's fine. She has no indication that there's anything amiss. Unfortunately, if we go to a command prompt, and we do an ipconfig/all, upon close inspection, we can see that she is not on the 10.123.0 network. She's on the 192.168.0 network. Her host ID is 198. Her default gateway, DHCP server and DNS server, is 192.168.0.1. Now, unfortunately, that is the rogue DHCP server, also acting as a router that I plugged in about an hour ago. And all I did was I took the WAN port on the D-Link and I plugged it into one port in VLAN 123 on the switch. And I took the LAN ports, now there's 4 Ethernet ports on the switch on the D-Link, and I plugged that into a second port on the same VLAN. So now this D-Link device has a valid WAN connection from its perspective. It's going to use the default gateway of 10.123.0.1. Maybe it was assigned a dynamic IP address on the VLAN 123 of 10.123.0.50 or some other valid address. And now acting as a DHCP server, it could be handing out 192.168.0.0/24 and anything in that subnet. And in fact, that's what's happening to this client right here. It's picked up an IP address from the incorrect DHCP server, and because I configured the D-Link with a valid WAN connection, we can actually route through the D-Link from Lois's computer right here out the WAN port. And most of the time, if the rogue DHCP server is accidental, this computer Lois, she'd be given the information regarding her IP address and default gateway and so forth, but it wouldn't have any success in going out to the internet if the rogue DHCP server was not also properly configured for routing and internet access itself. So on one hand, we have a denial of service attack regarding Lois's computer, and on the other hand, with full routing capabilities, we have the potential for a man-in-the-middle attack. So let's correct this problem. On VLAN 123, I've got on ports 5 and 6 on the switch. That's where the D-Link is currently connected. On port 3, I have a trunk port that goes up to, among other things, the DHCP server. Now, I happen to have an iOS router that's acting as a DHCP server. That's at the other end of this trunk. I also have on port number 1 a trunk that goes out to another environment. This all happens to be virtualized out here. And that's where the PC is. That Windows computer that we just looked at that had the incorrect IP address that was handed out by the D-Link, it's also on VLAN 123. And when we set up DHCP snooping correctly, because all these ports will be untrusted by default, the D-Link will be unable to do our offers and unable to do the acknowledgments and the other server-based DHCP functions. And that will allow the iOS DHCP server that's here to go ahead and respond if we configure this port, port number 3, as a DHCP snooping trusted port. So in our topology, this will be the only port that we need to specify as trusted. The other thing that we could do, however, is we could go over to ports 5 and 6, which are simply user ports, access ports, and we could make sure that port security is on there. Now, why? What's the benefit of port security? Well, in the previous video, we took a look at port security. We identified that it could limit the number of MAC addresses that could be seen off a port running port security. And let's say we set the maximum to 5 MAC addresses. What that's going to do, it's going to help protect against a DHCP starvation attack. So that if the attacker on one of these ports tried to do a DHCP starvation attack and started sending lots and lots of discover messages from different MAC addresses, because the switch would cut them off at 5, that's going to limit the number of requests that are coming in on any given port to that same number. So in the case of 5 maximum MAC addresses, that's also going to limit the number of DHCP assigned addresses, because with only 5 MAC addresses, the DHCP server is only going to be handing out 5 IP addresses. So port security, in addition to mitigating or reducing the risk of a CAM table overflow attack, it's also mitigating the risk of a DHCP starvation attack. Now, another option that we also have on these untrusted ports is we could set up rate limits for DHCP. And we could say, for example, no more than 10 packets per second regarding DHCP. And if we did not have port security configured on these ports, that might be one way to help slow down a DHCP starvation attack by specifying how many packets per second regarding DHCP traffic is allowed into that port. And because we have both features available, port security to limit the number of MAC addresses and rate limiting of DHCP traffic, it doesn't hurt to use both of those together. That way, at some point, if port security is removed for some reason, we'll still have some protection against a DHCP exhaustion attack if we simply slow down the rate. So on switch 1, we're going to go into configuration mode. We're going to enable the feature with the command IP DHCP Snooping. We're also going to tell it where to keep the DHCP Snooping database, also sometimes referred to as the DHCP Snooping table. And in that table, it's going to keep track of details such as what is the IP address that was handed out to that client via DHCP? What is the MAC address of that client? What VLAN is that client participating in? And those are all stored inside of this DHCP Snooping table or DHCP Snooping database. Now, in this demonstration, I'm going to simply put it on Flash. But why do you think that might be risky in a large environment with thousands of clients asking for IP addresses? And the answer is Flash is only so big. So in a production environment, instead of storing it on local Flash on this switch, we might choose to store that on a server. So if we use the magic of the up arrow key and go back just a little bit to take a look at our options, we have some great options. We have HTTPS, which is great. We have Secure Copy Protocol, which is great. And protocols like FTP, HTTP, and RCP, and TFTP are all plain text. So we'd want to avoid plain text protocols whenever possible to help protect the confidentiality and data integrity of data as it goes back and forth between our devices. In this example, between the switch and whatever server we're storing the DHCP Snooping mapping table. Another thing that would be great is to make sure that we have our time synchronized. We'll have another separate video on network time protocol, but it's a great idea in a network where we have multiple things happening to have time synchronization so that our timestamps are accurate. So if we need to correlate several different events from several different systems, it can give us a better representation of exactly when they happened if we know that the actual timestamps on those events are correct. Now, one of the challenges is this. Once we've typed in IP DHCP Snooping, we think, hey, it's enabled, but it's not enabled for the VLANs until you also specifically tell DHCP Snooping that you want it activated for a VLAN. So in our case, it's VLAN 123, so we'll type in IP DHCP Snooping, the keyword VLAN, and the VLAN number of 123. Now, it's enabled for VLAN 123. And that's because we enabled it on the box as a whole, and we've also enabled it on this VLAN. The interface that we want to go ahead and consider to be a trusted port will be the one that leads up to the DHCP server. And that is port 3 on this switch. So we'll go to interface gig 0/3, and we'll simply say, Dear Mr. Port, you get to be trusted from a DHCP snooping perspective. And what that does on port number 3, it allows inbound DHCP server messages like offers and acknowledgments, and any other typical DHCP messages that would be seen coming from a server going to a client. That keyword of trust says, I will allow them inbound, says the port, to go ahead and enter the network. And by default, the other ports, like ports 5 and 6 and everything else in that VLAN, are untrusted by default. We don't have to go to every other port and say, you're not trusted, you're not trusted. That's the default position, is just say no to server messages. Unless you have a trusted port, like we do right here with port gig 0/3. Now, although we don't have to do any additional special configuration for the user ports, they're untrusted by default, we can do a couple of details. For example, if we want to set up rate limiting for DHCP messages, these would be client type messages that are going into the switch, we can set that rate limit. In this example, we're setting it to 10, and that refers to 10 packets per second. Now, if we set this value too low, we may prevent a valid client from actually getting an IP address in a timely manner. So before setting that and saying, woo, we're going to help mitigate a DHCP server exhaustion attack by rate limiting DHCP on untrusted ports, you might want to consider doing a baseline, get a packet capture out, eavesdrop the traffic during a DHCP conversation, and see how much DHCP traffic there really is. because we might think, 10 packets per second, that's way more than we'll ever need. However, what if this is a trunk port? It's an untrusted DHCP snooping trunk port. And we have hundreds or thousands of clients that might be asking for IP addresses, especially at the same time in the morning. Maybe all the computers come on around 8 o'clock. There's a rush for the DHCP server. And if we're on a trunk and we're limiting it to 10 packets per second, that's very likely to cause some failures of getting a DHCP address by our clients. Now, in the previous video on port security, we configured port security on access ports. And it ties into DHCP snooping as well, because if we do port security where we're limiting the MAC addresses, that's also preventing from those ports a DHCP exhaustion attack, which is typically going to happen right before the rogue DHCP server is introduced into the network. So the port security is just a little bit of a reminder that that's a good idea to help limit the number of MAC addresses that are learned on a port. And so for these two ports, we've enabled it. We've set a maximum number of 5, and we enable the feature. So if we're using the default port security, if there is a violation, if a 6th MAC address does show up, the default violation is going to be to do a shutdown of that interface. So now as a test, let's go back to our client. This was Lois's machine who had been given an IP address from the rogue DHCP server. Let's simply disable the interface. And then we'll go ahead and bring it back up. That will cause it to go ahead and get an IP address again. Now when we bring this up, it may have done some background trying with the old DHCP server. However, the rogue DHCP server, because it's connected on the untrusted DHCP snooping ports, is now unable to respond. So now if we do an ipconfig/all, you'll notice that we have an IP address on the correct subnet of 10.123.0.3. Our default gateway is 10.123.0.1, which is the actual iOS router that's currently acting as a DHCP server. The DNS information was also learned via DHCP. So it looks like we're back on track. Now, if you want to lab this up, and I strongly recommend doing that, if you're using an iOS router as your DHCP server, and you're doing DHCP snooping on the switch, on the iOS router that's acting as the DHCP server, you'd want to add the following command: IP DHCP relay information trust. And that's specific, again, if you're using an iOS router. So if you're labbing this up and you're using an iOS router as your DHCP server, I would go ahead and add this to your router acting as the DHCP server in order to remove the obstacle of your iOS router that's working in conjunction with DHCP snooping from no longer being able to hand out IP addresses. Now we know that the client, Lois's computer, has got an IP address from the correct subnet, so that's a good indication. On the switch, however, we also could validate our DHCP snooping configuration with a show IP DHCP snooping command. So regarding interfaces that have any type of DHCP snooping configured directly on them, we have interface 3, which is a trusted port. 5 and 6 are not. And the reason that ports 5 and 6 are showing up here specifically is because they have the rate limit specified on them of 10 packets per second. If we wanted to take a detailed look and see what's in the DHCP snooping table or database, we'd use the command show IP DHCP snooping with the keyword binding. And what this shows us is that it's learned about 10.123.0.3 that was offered via DHCP and accepted by the client. The client that has that IP address assigned to it has this MAC address. That's Lois's computer that we just looked at a moment ago. There's how many seconds are left on the lease. It was learned via DHCP snooping. That client is on VLAN 123. And the switch learned about that client off of gig 0/1, which effectively is a trunk. So here's switch 1. There's port number 1, which is a trunk over to the virtualized environment, and the PC that we looked at as the DHCP client is in that environment. But the concepts would work the same, whether this is a physical PC or a virtualized PC. And that's what's so great about a lot of the technology that we're learning, is that as we start applying these concepts to virtual environments, we have virtual switches and virtual routers and virtual firewalls. And the concepts that we apply regarding security still apply in a virtualized space. So in our lab environment here, we're storing the snooping database, that table, on our flash. So if we do a directory of flash, we can see right there we have snoopy.db, that's what we called it. And the command show IP DHCP snooping database detail can be used to show statistics regarding that database. And it is time for our assessment check. So go ahead and take a moment, read through these questions, and we'll compare answers in just a few moments. what command, regarding DHCP snooping, what command shows the MAC address to IP mapping? So these commands are all going to start something like show IP DHCP snooping space, then something. To see the MAC to IP binding, what we demonstrated in the nugget was the keyword binding. So show IP DHCP snooping binding will show you that MAC to IP mapping. Question number 2, what command shows the statistics for the DHCP snooping database? And in the nugget, I had a pop out that showed the option for seeing statistics, and it's actually the keyword of database. So the command show IP DHCP snooping database will give us statistics regarding that database. And then question number 3, how does port security help with DHCP issues? And the benefit there is that we can help protect against DHCP starvation attack by limiting the number of MAC addresses that can be learned on ports that are being protected with port security. At the beginning of this nugget, we discussed that it's important not only to understand the concepts, but also to implement features such as DHCP snooping. And that's exactly what you and I have done in this nugget. And I would encourage you, wherever possible, to practice these on your own as well, to build your skills and get better and better using the tools of security that Cisco has available to us.